Okay, today is about solubility of molecular substances in, so we're talking about why certain things dissolve in each other and why certain things do not. And I want to take us back to the experiment I did for you a couple of days ago to talk about this. So in that presentation we had ethanol, and I really want to just start by asking you to think about, well, why does ethanol dissolve in water, and how could you even make a sense of that? Methanol was another one. Hexane. I'm not going to put turpentine in here because it's such a big molecule. Sugar, though, I will put in because of something else. And of course, water. I could also talk about oils and fats here because of something else also. So the formula for ethanol is C2H5OH. Methanol is CH3OH. Hexane is C6H6, no, C6H14 actually. Sugar, C12. This is sucrose we're talking about. H22O11. Water, of course, H2O. And oils and fats are just really extremely long hydrocarbons, C18H38 or equivalent to that. So how do we draw the Lewis structure for these? We'll get you to the point where you will then start to understand why ethanol and methanol dissolve in water but not in hexane. Sugar dissolves in water, but hexane would dissolve in oils and fats. So remember, when you're doing Lewis diagrams, you leave hydrogen to last. You put the least electronegative in the middle. So this would be the two carbons, and we're just going to connect them. Then you're going to put the oxygen, and now you're going to put the hydrogens around this so that they complete the octet of the carbon and the oxygen. And when you do this, you can see now that everything has a complete octet. So, you know, there's 6 and 6 are 12, plus 5 is 17, plus 1 is 18, plus another 6 is 24, which is 12 electron pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I've done some math wrong here. 4 and 4 is 8, plus 5 is 13, 14, plus 6 is 20. So that's the 10 electron pairs there. Methanol, same thing. Carbon and oxygen. Now the hydrogens go around to complete the octet. And so we've got 4 plus 3 is 7, plus 6 is 13, plus 1 is 14. That's 7 electron pairs. That's 1, 2, 3, 4, 5, 6, 7. This is just a straight chain of carbons. It's not really straight. It doesn't do it justice drawing it in linear. And then you just put hydrogens around to fill the octets. This is a hydrocarbon. You'll get to know hydrocarbons in detail in the organic chemistry. Sugar is a real interesting molecule. So it's a molecule that has a hex like so, joined to a so this is a glucose molecule which is joined to a fructose molecule like so. And actually this is not quite drawn correctly. This should come to a C here, and that O is on that C. There's a CH2 OH group here. There's an OH group here, and an H, an OH group here, and an H, an OH group here, and an H. And over here there's CH2 OH, an OH group here, and an OH group here. Then of course water has just the regular Lewis diagram that you're all used to drawing by now. And then these are long hydrocarbons similar to hexane but just much larger. Now to talk about the polarity of this, you've got to talk about each carbon, each of these atoms independently. So this would be tetrahedral, this would be tetrahedral, but this would be bent tetrahedral. So in fact the molecule is best drawn like this. And what's going to happen is that this is going to be negative here, that's going to be positive, but the true tetrahedrals here will be symmetric and non-polar. Now as it turns out, there's enough difference in the oxygen and hydrogen to give ethanol a polarity. So it's a polar molecule. And the same with methanol. It just has that O like that. So the carbon is non-polar. So it would have a non-polar piece down here, but the oxygen is, and the electrons are getting drawn up to there. So again, methanol is a polar molecule. You've got to be careful with these alcohols because the bigger they get, one end of them becomes non-polar and one end becomes polar, and that causes a difference in their solubilities. This, of course, each carbon here in hexane is tetrahedral. 4 regions of negative charge around each of these carbons here, and so this will be a non-polar molecule. Overall, there's no, each of the carbons are symmetric, all the dipoles cancel, whereas here the dipoles cancel there, but in this part of the molecule they don't, and that gives it its polar nature. Now sucrose, as you can see, has lots of these OH groups around, and these OH groups are polar, all of them. So sucrose is a polar solid. It's a molecule. So all of these are molecules. This is just a big molecule. That's why it's solid at room temperature. And it gives it its special dissolving properties. Now, if we go and look at water, we know that that's polar. And these, of course, would be non-polar. All oils and fats are non-polar molecules. The biologists, you need to be able to understand this bottom piece here, because you're going to be starting to talk about hydrophobic and hydrophilic as well. So that's how we draw the Lewis diagrams for each of these bigger molecules. And then if we remember back to the experiment we did the other day, we can now draw a table of the solubility of these molecules in water and in hexane. So we can draw up a table. Oops, this is not going to be a very good table by the looks of it. I might just start again, and I'll just put the substance ethanol, methanol, hexane, sugar, water, and I will put the oils, the fat oils down here. So if I draw a line there, we'll just describe. So this is polar, this is polar, non-polar, polar, polar, non-polar. Now, so there's solubility in water. So we're looking at solubility. Water. This is yes. And we would call it miscible, because you can put any amount of ethanol in water and it will remain soluble all the time. Same with this, yes and miscible. But this is no and immiscible, and you saw that because it formed two distinct layers. And that, if you go back to that video and look, sugar is soluble and is miscible. Water, we don't really need to talk about that. And this is no, and this is immiscible. You've seen oil and water before, but there's another video coming up that will highlight this. So that forms a layer also in hexane. We got yes for this, and there's a special reason for that, but this was no, immiscible, this was not, sugar would not, it would just sink to the bottom, and it would be immiscible. Water, no, immiscible. two layers forming. Oils and fats, yes, they would dissolve, and they would be miscible. So the question is, why does this happen? And if you look at that, we've got a polar solvent here, a non-polar solvent there. And if you look at this, the polar ones are dissolving in the polar solutes are dissolving in the polar solvents, and the non-polar solutes are dissolving in the non-polar solvents. And this leads us to this idea of likes dissolve likes. Likes dissolve likes. This is the rule of solubility, really. If you can understand that. So, non-polar solutes, solvents dissolve non-polar solutes. Polar dissolves polar. And an interesting here is that polar solvents also dissolve ionic salts. And if you think about that, because these have got ions in them which are charged, then they will dissolve because the polar end of the molecules can react or interact. And we'll talk about why this happens later. So, if we go to this, so there are some terms that you need to understand here. Solubility measures how much of a solute is being dissolved into how much of a solvent. Solutions, you have to remember, true solutions are homogeneous mixtures. And you have to remember that dissolving is a physical process. And this is because you can get the solute and the solvent back again. So think about evaporation of a salt solution or distillation of whiskey or something like that. Solute is the substance that is being dissolved and is present in the smallest quantity. Solvent is the substance that is doing the dissolving and is present in the largest quantity. So dissolving is a physical change and leads to an even distribution of solute particles dissolved in solvent particles. So they're evenly mixed, they form new attractive forces that hold them apart from each other. Molecular substances, there are some rules that cover this. So as the word miscible is the property of two substances to mix in all proportions, no matter what the concentration, forming a homogeneous solution. Immiscible is incapable of being mixed together, and liquids are shaken together and eventually separate out like oil and water. So you can see in this diagram here, we've got a homogeneous mixture of ethanol and water, and we've got a heterogeneous or immiscible mixture actually of oil sitting on top of water. So here are the rules. Likes dissolve likes. Nonpolar solvents dissolve nonpolar solutes. Polar solvents dissolve polar solutes. And ionic salts will dissolve. And I'm going to talk about the interaction of the forces here in a different video.